This module on formation evaluation, MWD/LWD, and mud logging is designed to give you a clear understanding of how we acquire, interpret, and apply data during drilling operations. Formation evaluation is the science of assessing the subsurface through direct and indirect measurements. In our industry, it's critical for determining reservoir properties, fluid content, and wellbore conditions. Mud logging complements this by providing continuous surface-based monitoring of drilling parameters and cuttings. The combination of formation evaluation and mud logging helps reduce uncertainty and improve decision-making while drilling. Throughout this session, we'll connect the theoretical principles with practical applications, showing how logging tools and surface measurements work together to provide a comprehensive picture of the well. We'll also highlight the strengths and limitations of each technique, ensuring you have a balanced understanding. This presentation is the first of 3 sub-modules. By the end of this module, you should be confident in several core competencies. First, we are going to focus on measurement while drilling, MWD. You will also learn the fundamentals of how these systems function, including their data transmission methods and sensor applications. Importantly, we'll explore the advantages and disadvantages of MWD, equipping you to weigh their use in different operational contexts. In the next submodule, we will examine LWD technologies, and in the final submodule, we will explore mud logging principles and applications. When we talk about MWD, or measurement while drilling, we are describing one of the most critical technologies in modern drilling operations. The MWD tool is designed to sit close to the drill bit and continuously gather downhole data. What makes it so powerful is the ability to transmit this information in real time or near real time to the surface. This means that as drilling progresses, the directional team and the geologist can immediately see what's happening downhole rather than waiting until the pipe is pulled out. The most common data delivered by MWD includes inclination, azimuth, and tool face orientation, parameters that are essential for directional drilling. In addition, MWD services can provide gamma ray readings, downhole temperature, and annular pressure measurements. These inputs are vital for both geological evaluation and operational decisions, such as hole cleaning efficiency. It's important to distinguish MWD from mud logging. Mud logging provides surface-based observations through cuttings and gas detection, whereas MWD delivers precise, depth-specific downhole data. While mud loggers may detect more about rock composition through physical samples, MWD offers unmatched immediacy and accuracy in directional control. In the next slide, I will guide you through a video demonstration of the MWD tool. So let's progress. MWD stands for measurement while drilling. These measurements help us determine the orientation of the drill bit, which in turn allows us to calculate the position of the wellbore and steer the well as drilling progresses. Importantly, these measurements are taken in real time while the well is being drilled. The most common type is a magnetic MWD tool, which relies on measurements of the Earth's magnetic and gravitational fields to determine the orientation of the bottom hole assembly. You can think of it much like using a compass to find your bearing. The tool has 3 magnetic sensors, each placed at 90 degrees from one another. These measure the Earth's magnetic field and are typically referred to as B, X, BY, and BZ, where the BZ sensor aligns along the hole. In addition, the tool also includes 3 accelerometers, arranged in the same way, to measure the Earth's gravity field. These are labelled AX, AY, and AZ, with AZ again along the hole. The accelerometers not only give us orientation relative to vertical, but also serve as a reference for the magnetometers. Together, these magnetometers and accelerometers form the sensor package of the MWD tool. Beyond sensors, the tool has a telemetry section responsible for transmitting the data back to surface. The most common mode is mud pulse telemetry, where information is encoded into the drilling fluid as a sequence of pressure pulses, very similar to Morse code, and then decoded at the surface. Other transmission methods include electromagnetic telemetry and wired drill pipe, though each has limitations. The tool also requires a power source, typically provided either by batteries or turbines that generate energy as drilling fluid passes through them. The MWD tool is usually programmed to take surveys at connection times when mud flow is stopped and the bottom hole assembly is stationary. Finally, the tool is located in the bottom hole assembly itself, encased in a non-magnetic drill collar. Ideally, it should be placed as close to the bit as possible, though often it must be positioned some distance away, sometimes 60 feet or more, to avoid magnetic interference or damage in harsh drilling environments. So, in summary, an MWD tool is best thought of as a compact package consisting of sensors, telemetry and power, all designed to continuously measure and transmit downhole data while drilling is underway. MWD tools come with a wide range of features, many of which are essential to safe and efficient drilling operations. At their core, MWD systems provide directional data, azimuth, inclination, and tool face, which allows the directional driller to steer the well accurately. They also provide annular pressure and downhole temperature readings, important for monitoring wellbore stability, fluid properties, and equipment performance. Some MWD tools can detect shock and vibration, enabling crews to recognize harmful downhole dynamics that could damage tools or compromise drilling performance. When additional modules are installed, MWD systems can capture gamma ray, downhole weight on bit, torque, and even more advanced parameters. Another critical feature is real-time telemetry, where MWD data can support the transmission of LWD measurements. There are several types of MWD tools, and understanding these categories helps us select the right tool for the job. One key classification is retrievability. Retrievable tools can be recovered and replaced without pulling the entire drill string, offering flexibility and reducing costs in case of failure. Their downside is limited connectivity to advanced sensors and a lower level of reliability. Non-retrievable tools, by contrast, offer multi-sensor capability, often including resistivity, caliper, and other advanced measurements, but require a full trip if a failure occurs, increasing costs and downtime. Another way to classify MWD is by telemetry method, or how the data is transmitted. Mud pulse telemetry, electromagnetic EM telemetry, and wired drill pipe each have unique strengths and limitations. Mud pulse is reliable but slower. EM offers independence from mud systems but can be depth limited. Wired pipe provides high bandwidth but requires specialized infrastructure. Telemetry is the lifeline of MWD systems, and here we compare the three main approaches: mud pulse, electromagnetic, EM, and wired drill pipe. Mud pulse is the most widely used, sending pressure signals through the drilling fluid, typically at 0.5 to 1.5 bits per second for pulse systems, or up to 12 bits per second with carrier wave. It's simple, reliable, and works well in most drilling environments. EM telemetry transmits data through the formation itself, independent of mud properties. This method can achieve 3 to 12 bits per second, but performance is limited in conductive formations or at great depths. Wired drill pipe represents the most advanced option, with inductive couplings at each tool joint providing bandwidths as high as 56 kilobits per second. This allows near instantaneous transmission of complex datasets, ideal for high-value wells where precision matters. Each system has its advantages and trade-offs. Mud pulse is rugged and cost-effective, EM is fast and flexible, and wired pipe is powerful but expensive. Mud pulse telemetry is the workhorse of MWD communications. It operates by creating pressure pulses in the drilling mud, which are detected at the surface and decoded into data. There are three main types of mud pulse telemetry. Positive pulse works by restricting mud flow to create a pressure spike. Negative pulse does the opposite, momentarily venting to reduce pressure. Carrier wave telemetry uses continuous oscillations in mud pressure, with data encoded through phase shifts. Each method has unique advantages. Positive pulse is robust and widely used. Negative pulse minimizes flow disruptions, and carrier wave offers higher transmission speeds. However, mud pulse overall has limitations, particularly in terms of bandwidth, typically less than 12 bits per second. For this reason, it's best suited for transmitting essential drilling and directional data rather than complex formation evaluation. Despite these limits, mud pulse remains the dominant telemetry method worldwide due to its reliability and adaptability. Electromagnetic EM telemetry offers an alternative to mud pulse, transmitting signals directly through the formation rather than relying on fluid pulses. This method provides the advantage of being independent of mud properties, making it especially valuable in underbalanced drilling or with air and foam drilling systems. EM telemetry typically achieves speeds of 3 to 12 bits per second, faster than conventional mud pulse, though less than wired pipe. One of its limitations is attenuation in conductive formations, such as shales or salt, which can reduce signal strength and reliability. Depth also presents a challenge. EM signals weaken significantly at greater depths. Despite these limitations, EM telemetry is an important tool for specific operational contexts. When conditions are right, it provides faster, cleaner data transmission than mud pulse. This system is commonly used in land operations with shallow wells, for example, in the US shale plays. Because the receiver must be staked into the ground, it is not possible to use an offshore option. MWD tools require reliable power sources to operate downhole. There are two primary systems, turbine power and battery power. Turbine-driven tools generate electricity from the flow of drilling mud. Their advantage is a virtually unlimited supply of power as long as circulation continues, making them suitable for long runs. The downside is that they stop producing power when pumps are off, limiting functionality during connections or trips. Battery-powered systems, typically lithium-based, enable continuous measurement of whether circulation is active. This is especially useful for capturing data during static conditions. However, batteries come with challenges: limited run life, sensitivity to high temperatures, reduced power capacity, and safety concerns in handling. Additionally, the batteries must be disposed of in an environmentally friendly manner. Currently, there are only a limited number of processing facilities worldwide. Selecting the right power source depends on well design, expected drilling conditions, and tool requirements. As a driller or engineer, it's critical to appreciate these trade-offs. Turbines deliver endurance, while batteries provide flexibility. Weight on bit is a fundamental parameter in drilling operations. MWD tools measure weight on bit using strain gauges fixed to the drill collar. These gauges detect stretching and compression as forces are applied downhole. When weight is applied, certain gauges skew or compress, while others stretch, altering their electrical resistance. This change is translated into a direct measure of force on the bit. Monitoring weight on bit is essential because it directly affects drilling efficiency, rate of penetration, and bit life. Too little weight reduces drilling performance, while too much can damage equipment or lead to wellbore instability. Torque at bit is closely related and is also measured using similar gauges. Understanding how downhole weight and torque at the bit give drillers insight into how the weight is being transferred to the bit from surface. Poor transfer could indicate issues with hole cleaning or wellbore instability. Directional MWD sensors are at the heart of accurate wellbore placement. These systems rely on an array of 3 orthogonal accelerometers and 3 orthogonal magnetometers. The accelerometers measure the Earth's gravitational vector relative to the tool's axis, allowing calculation of inclination and tool face orientation. The magnetometers measure the Earth's magnetic field components, which, when combined with accelerometer readings, determine azimuth. Together, these 6 sensors enable full 3-dimensional positioning of the wellbore. The concept of the scribe line is also important. It provides a reference orientation from the high side of the bend in the motor to the reference point on the MWD tool. This is an offset applied to the software to ensure the MWD is correctly aligned with the motor. This offset measurement is performed at the beginning of each run at the surface. It must be witnessed by the directional drilling and the company representative. An incorrect entry can lead to a steering offset. For directional drillers, this data is crucial in keeping the well on plan and preventing collisions. This applies to motors and turbines where there is a bend, but not to rotary steerable tools. Advances in sensor technology have improved precision, reducing the discrepancies between survey while drilling and static survey measurements. Some rotary steerable systems even allow true at the bit inclination and azimuth readings. Wellbore surveying is one of the most critical tasks in directional drilling, and MWD tools play a central role in this process. However, it's important to remember that MWD measurements are taken some distance behind the bit. This means the data always lags slightly behind the actual bit position. While inclination and azimuth readings from MWD provide a reliable survey of the drilled hole, they cannot always tell you the precise, instantaneous location of the bit. This is where advanced systems like rotary steerable tools with true-at-the-bit sensors come into play. Still, conventional MWD surveys are invaluable for ensuring the well follows plan, avoiding collisions and maintaining accuracy. Inclination at the bit is particularly useful for drillers as it allows them to make fine steering corrections in real time. Let's review the objectives we set out at the beginning of this module. You should now be able to define an MWD, explaining its principles and applications. You've learned the fundamentals, including data types, telemetry systems, and sensor arrays. Thank you for engaging with this submodule. Please progress to the quiz.